This is 5 Minute Friday number 3, and today we're going to be measuring and inspecting angles using a sine bar. This is part of the sliding block assembly, which has a critical angle of 15 degrees on this taper here. So we need to inspect this edge to check that it falls within our 0.15 degree tolerance. So to do this, we're going to need a set of gauge blocks or slip gauges, and we're also going to need a tool called a sine bar. And the sine bar that we'll be using is a 100mm metric sine bar, and that's going to allow us to measure the angle. And the principle of this is that we're going to create a stack of slip gauges on the right hand side, incline it at an angle, and then the sine bar can be used either to scribe lines in layout, or it can be used to inspect angles with a dial test indicator. So this is an image of what we're trying to achieve. We're trying to incline the sine bar at an angle of 15 degrees so that when we run the finger type DTI across the top of the surface, we can check for any movement, and this surface should be flat. So it's called a sine bar for good reason, because these points here are exactly 100mm. That's the hypotenuse of a triangle. The slip gauge stack is the opposite side, and we form a triangle there. So we need to apply a bit of secondary school or high school trig to find the exact height of slips required to create the 15 degree angle that we require. So you probably remember. So SOH, sine 15, equals the opposite, which is our slip gauge pile here that we don't know, we're trying to find that out, over the hypotenuse, which is this known distance, is 100mm sine bar, so that is 100mm. And we can rearrange that to get sine 15 times 100 is equal to the slip gauge height that we need. So we'll need to put that into a calculator. If you're not sure how I did that, if you're not too familiar with trigonometry, then you can just use a equation triangle here. If you're not so good with transposing equations, cover up the O, and it's sine times h. If we needed to find the angle, it'd be the opposite divided by the hypotenuse. So let's chuck that into a calculator. There we have it. So we've got 15 sine times 100, and it gives us 25.8819. Our slips will measure to the thousandth, so we're going to use 25.882. 25.882mm. So what we need to do now is pull those out of the slip gauge pile, and to do that we'll start from the right. We'll have a 1.002, a 1.08, a 1.8, and 22mm of other slips. Once we've chosen our slips, we need to ring them together, which means basically put them at 90 degrees and twist them with a little bit of pressure, and they'll stick together due to molecular attraction. Now what I'm doing here is actually bad form. You shouldn't put them in contact with the surface plate, and certainly not slide them like I did, but we're showing the point that they will stick together to create the accurate height. Once we've got the slip gauge pile, we can place that against an angle plate. That section, I guess, is unnecessary but helpful for getting everything squared up. Now I'm going to use 2 sine bars as opposed to one thick one. Don't have one single thick one, and we're going to support our sliding block on top of there. Now if everything goes correctly, then we should create a flat surface there due to the two 15 degree angles. And what we'll do is we'll run a dial test indicator across that top surface so that we can check whether it's running out or not. If it doesn't run out, we'll get a reading of 0. So we need to line up our DTI so that the finger is roughly at an angle of 20 degrees or so when we first start. That way, when it makes contact with the block, it's near enough horizontal, and that's going to reduce sign error. Then we can move it back and forth. Once we're happy that it's in correct contact, we can zero out the gauge for a setting, run it back and forth once again, and make adjustments to the slip gauges on the right hand side so that it does actually run flat true. So here we can see it's actually raising a little bit, so it's probably a little bit low at the bottom there. So we need to add slip gauges to reduce that error. So now we're faced with a situation where we know the opposite side, so perhaps we've adjusted that to 25.951, and that causes it to run flat, which means now we've knocked this angle out. So we're actually going to find out what this angle is here. So this is an unknown angle, and the convention is to call that unknown angle the Greek letter theta. Okay, so we're still going to use, in essence, the same type of equation, but this time we need to find the sine theta. So sine the unknown angle theta is equal to the opposite, which in this case is 25.951 divided by 100. So we need to process that, and to find out theta we're going to use the inverse sine of this, which should be 0.25951. Again, we'll put that in the calculator. 25.951 divided by 100. Sine to the -1, so inverse sine to -1. So the angle that we've actually inspected there isn't 15 degrees, but 15.041, which is amazing considering with so little equipment we've managed to inspect to 1/1000 of a degree.